All right. Okay. Now I can hear myself. Let's try that again. So, good evening, everyone, and welcome to the May 2024 Meet the Astronomer lecture. Before we begin, just a couple of announcements. We have summer camps, which are now full. We do have a wait list going, so in case we do have some folks that unfortunately cannot come, we'll have some other folks that can take their place. So you're welcome to join the wait list if you've got a rising 5th, 6th, 7th, or 8th grader that's interested in space science. And just keep an eye on that wait list. So we do have additional events this year, including additional Meet the Astronomer lectures, telescope nights. We've got Bluebird on the Mountain concerts coming up. And if you want to get tickets for those, just go to our homepage, and if you scroll down a little ways, you're going to see some of those upcoming events, and there's a button on there that says Buy Tickets. You click on that, that's going to take you to our main ticketing page, which is Eventbrite, and that'll show you all of the various events that we have lined up so far for this year. And at the top of that page, there's a little blue button that says Follow. Click on that, and that will get you added to a list where if we add any event to our schedule, you'll get an instant notification about that. So we'd highly recommend y'all try that out. The program for tonight, that's going to last about 45 to 60 minutes, and then we'll open up the floor to a Q&A session afterwards. So if you've got some burning questions, just hold those to the end there, and we're going to take care of as many of those questions as we can. In addition, we are live streaming this to YouTube right now so that folks from afar will be able to enjoy this fabulous lecture and be able to answer questions or get questions answered as well. So for those that are watching on YouTube, if you get a question, just go ahead and pop it in the chat whenever it pops in your head, and we're going to get as many of those answered at the end as well. And then after the program, especially for those that are here for the very first time, if you'd like to go up and see the big telescope, you are welcome to do that. We'll have volunteers up there that'll be there to answer questions and tell you about the telescope. And if it ends up being clear enough, we'll do a little bit of viewing afterwards. So we're going to keep our fingers crossed those clouds will move out of the way. So I'm thrilled to introduce our speaker tonight. Dr. Erika Grundstrom is Vanderbilt University's Director of Astronomy Labs and an experienced educator whose kids may have had, let me try that again, and an experienced educator who kids may have had as a teacher in Vanderbilt's program for talented youth. Or seen with an inflatable portable planetarium that she's taken around the Nashville area. And I can't tell you how many shows she has done, probably literally hundreds. Yeah. So as a kid, she lived on a farm close to the Canadian border where she thought the northern lights were normal. And hopefully you all got to see those just recently.
There is a real, if you haven't seen it, there's a really awesome time lapse that Dr. Billy put on YouTube for everybody to see. It's totally cool.
So yeah, that was my first really good view of the Northern Lights. So, but it was learning about the constellations and the mythology with them that sparked a love of the stars, and then Star Trek: The Next Generation. High five.
Nice.
Yeah, right.
Yeah.
And that set her on a path to be an astrophysicist. So when not astronomy-ing, she loves to partner dance with her hubby and hang with their 2 kids. So I came to know Erika when I was at Vanderbilt as a grad student finishing up my PhD program, and she had just come to Vanderbilt. And I have to say that I've always been thoroughly impressed by her tenacity, her enthusiasm, and her commitment when it comes to teaching, either fourth-year undergraduates in a classroom or a bunch of elementary schoolers in the inflatable planetarium. So I think you're going to have a great time with us tonight as she talks to us about amazing moons. So please join me in welcoming Dr. Erika Grundstrom.
Thank you very much, Billy, for that awesome introduction, and welcome everyone. I'm so excited for us to explore some of the solar system together. Now, I will be asking you to do things kind of during this presentation, like I'm going to show you some things, and then you're going to try and make some determinations and things like that. So I really hope that you'll get to really think about how amazing moons are. And, there are so many amazing photos or images out there. but they don't tell the whole story. There's all sorts of awesome physics, and there's awesome just like possibilities that are out there for thinking about these moons. So the background here in this is actually an older image from NASA, and it shows most of the rounded moons of the solar system. So ones that actually don't look like potatoes, because if you're thinking about things that are small, generally, if small things like asteroids especially, if you think asteroid, you should think potato. So if I say asteroid, you say? Potato. Right. So we're going to mostly be looking at the rounder moons, but realize that there are a whole bunch of other moons kind of out there as well, little ones. Okay. So I kind of like the way that I'm kind of doing this is like the moons of the solar system are teachers to us. So we can learn about all these different things. We can learn about the worlds that these moons go around. We can learn about ages on surfaces, and that can tell us a lot about the geology and kind of the interiors of those worlds. Some of this stuff, of course, works for planets as well, not only moons. We can also learn a whole bunch about planetary formation, and I'm going to show you some of that stuff. I'm going to show you some awesome images and things and ideas. And then I'll talk a little, hopefully we'll have enough time to talk about possibilities just kind of out there. So let's think about parent worlds. Now the reason I say worlds, by the way, is because I want to include as many things in the solar system as possible. So we're talking about planets, we're talking about dwarf planets, talking about asteroids, minor planets, right? There are all these little things, and there are definitely debates on the nomenclature, like all the naming, because especially some people who are planetary scientists are really are thinking about moons, especially ones that are rounded, more as we should call them satellite planets, or we should call it like dwarf planets. They are like planets, except we put a word in front of it to say dwarf planet, or we have minor planet, or there's a lot of very active stuff going on. So I'm going with like one of the more common ways we name things, just so you know, but there's a few other ways. And you can always talk to me about that afterwards, especially. I love to talk about this kind of stuff. So anyways, so looking at our parent worlds. So let's say you just have a telescope and you look at a thing. This does happen to be, I don't know, does anybody know what this one is? Yeah, say it loud. Yeah, Jupiter. This is Jupiter through a telescope. And so I've got my like laser pointer on here. But anyways, so this is like Jupiter through a telescope. So you can't really tell much about the moons themselves, but you can tell something about the positions. So if you look at this night after night after night, you're going to see like the four little things. There's 1, 2, 3, 4. You're going to see those four little things move. So then you can figure out an orbital period. So how long it takes that moon to go around that planet or world, go around that world. This happens to be a planet. And then if you do more telescopic observation, you can figure out something more. But we are going to do a little thing that brings me to my very favorite equation in all of astronomy. And, Stephen Hawking said in his book, Brief History of Time, every time you put an equation in a book or whatever, you lose half your audience. All right. I hope we're not going to do that, right? I only have one equation. All right. But it's the best equation in all of astronomy, in my opinion. Okay. So we are going to first think about how the orbits of these of the moons can help tell us something about the world itself. So let us look at these two pieces of data. So we got our one column is orbital period, and then the next column is how far away this moon is from its planet in lunar distances. So we're looking at the distance between the Earth and the moon as our measurement stick. Okay? Now, let's just think about something here. Do you guys know, like, how far away the moon is from Earth? Yeah. I mean, you know, we can say, like, it's a certain number of miles or a certain number of kilometers. So, but we could also be thinking about, like, the Earth and the moon kind of compared to each other. So if my head is the Earth, about how far away do you think the moon should be? Think it should be back there? Should be way back there? 24 million miles? That's an option. Right, but my head, my head's not that big, right? But, all right, so should the moon, if my head is Earth, should the moon be here? No. No? Yeah? Yeah? You know what, let's do a little show of thumbs. If you think it should go farther away, you're going to do thumbs up. If you think it should be closer, thumbs down. If you think it's about the right place, go thumbs even. Okay, so let's say head here, right? So should the moon be here? What are you thinking? Farther away, closer? It looks like people want to go farther away. All right, here I'm going to come out. All right, what about, like, if my head were, you know, let's just say my computer is Earth. Do you think moon here? Thumbs up if you think I should go farther away. I actually should go farther away. All right, what do you guys think? Yeah. There? I actually do still need to go farther away. All right. Okay, remember, head is Earth. Okay. So, here. So, do you think I should go farther away? Am I about at the right distance? Do you think I should be, well, you know, I already told you I can't be closer. Like, it's too far. All right, so do you think I should go farther, is up, or about the same? About here? I actually should go farther. Yeah. So, there are, if you put Earths side by side by side, there are about 30 Earths in between the Earth and the moon. This is like an awesome number to think about. Okay? So if my head were Earth, in order to be like 30 Earths away, this would be about the distance between me and the podium. Okay? So when we're talking about lunar distances, that's like really pretty far. It's way farther than you think. I love doing this with Play-Doh. Take a thing of Play-Doh, and then you can make like some little Earths or whatever, or you can just do, you know, you could just make a measurement, whatever. Take a ruler. But put 30 of the, whatever your object is, 30 in between. You can, like, if you have a couple of, you know, basketballs or something like that, you could go 1, 2, 3, 4. It's totally amazing to try and do this, to think about how far away that moon is. Now, if we're going to be taking these worlds at about, each of these different moons is about 30 Earth diameters, so Earth widths, 30 Earths, away from its parent world or parent planet. Now, I've covered up the planet names, okay? Just so you can see, I want you to try and look at a pattern. All right, I want you to try and think about a pattern. So all 5 of these are different worlds, okay? I want you to talk to at least one other person, and you're going to try and figure out, or maybe you could talk to somebody behind you or something like that too, right? Forward, and you know, let's like try and get a little bit of togetherness here. I want you to try and figure out which of these worlds has the greatest mass. Which one has the least mass? And how do you know, given just this information? By the way, what is orbital period?
The distance between.
No. Yeah. How long it takes for that moon to go around that planet? Okay? Talk. Are there any questions or clarifications anybody wants me to make now that they've been looking at it?
Can we get just, I think you already said this before, just to make sure. The first one is for Earth here, right? Okay.
All right, folks, let's have a little discussion here. First of all, which planet has the moon in the top row? Earth. How do you know that? It's 1 lunar distance, right? And then now let me just say something. I really have to say something about the orbital period of the moon, otherwise known as Luna, by the way. This orbital period says 27.3 days. We normally think of a moon orbit as the time from one full moon to the next full moon. And that's 29.5 days. There is a slight, the way that this orbit is defined is when the moon gets to in front of the same star in the night sky. Right, so let's say it was going in front of Arcturus, or not Arcturus, Aldebaran, or something like that. So it's just going in front of a star. It's like, when does it come back around to being in front of that star again? The reason there's a difference is that's called the sidereal orbit, and then there's a synodic orbit. But the full moon to full moon, Earth moves in its orbit, our year, it moves a little bit in the orbit. So in the month that it takes the moon to go around Earth, it takes the Earth has moved a little bit in the orbit. So we go a little farther. So we like to use full moon to full moon, and that's why we have a moonth, which is about 30 days. It is a month. But that's why this says 27.3 days, right? Because it's a slightly different measurement. But it is the same way that we measure the orbital periods of all of these other moons. So I just wanted to say that about that one right there. So which one of these is the most massive? Or has the most massive thing? Yeah, what do you think? The last one that has a 5.9 day orbital period, moon. Cool, we got that one as an answer. That may or may not be right. Anybody else want to hazard a guess? Yes?
Probably the second one.
The second one that has the 1.8 day orbit?
Yeah.
That may or may not be right. What do people think? Now there's a reason why I gave you all orbital period and then have all of their orbital distances about the same. So this is like a variable that we're not changing, right? So we are not changing the orbital distance variable, and we are changing the mass of the parent world, which will then change the orbital period. So a heavy, really gravitationally heavy thing, one that has the most mass, is going to fling its planet around really fast. Okay? So the bigger the more mass the planet has, the shorter orbital period its moon will have. This is our relationship. So this is why I didn't give you the planet names and the moon names. Now I had to find a couple of them. Oh, of course, Titania is a little bit awkward there. But here are the masses. Yeah, you got it up here. Nice job. Very nice, very nice. With snaps, right? With snaps. So Io has a moon that is about the is a moon of Jupiter that is about the same distance from Jupiter as as Luna is. But that moon goes around in only 1.5 days. Oh my gosh, right? So this means that something has to be flinging it around faster, and that's where the more gravity. We could talk about space-time curvature in the same way if you want to work with that definition of gravity. We'll go with just they're pulling harder for right now. So you may also notice you could tell the difference between Uranus and Neptune. We usually call them twins. I like to call there's certain things in the solar system that are twinsies, right? So Earth is a twinsy with what? Venus, right? So Venus and Earth are about the same mass, just about. We are also a twinsy with our moon because we're the same distance away from the sun, but we'll talk about mass twinsies, okay? Mercury has a twin. It's not Mars. And it's not Pluto either. It's actually our own moon, Luna. Really? Luna and Mercury are mass twinsies, which is kind of crazy to think about. We usually call Jupiter and Saturn twinsies as well. They're gas giants. They're about the same radius, but they are not the same mass. I mean, they're pretty close, but they're definitely not the same mass. And then Uranus and Neptune, we do call they're twinsies. We do call them ice giants. So we don't gas giant is not a great word for them, but ice giant is a great word for them because they have a lot more ices as a proportion of their interior than Jupiter and Saturn do. But anyways, you can actually tell the difference between their masses given the two moons that I've chosen for you. So you can actually do this with any moons in the solar system, or honestly, with any stars. You can look at stars having planets go around them, or stars having other stars go around them, which are binary star systems. We can do this with galaxies. We can figure out the mass of a world by looking at the stuff going around it. And this is how astronomers figured out the mass of the supermassive black hole at the center of our galaxy. Looking at stars orbiting that supermassive black hole, and they used this equation. This is the most awesome equation in all of astronomy, arguably, okay? So this is Kepler's third law, Newton's version. So the things that you need to know. On the left, orbital period. So how long it takes the thing to go around the other thing, the orbiter to go around the orbitee. And then we've got some constants. What's pi?
3.1.
Yeah, 3.14, 16, blah, 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 whatever. And then big G is the gravitational constant. Okay, so that has a number to it. 6.67 times 10 to the negative 11, blah, 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 with units, whatever. And then we've got a couple other variable things. In the parentheses up here, we have A, which is the average distance to the gravitational source. So it's kind of like the radius of an orbit. It's really called the semi-major axis, but that you're taking into account elliptical or like oval-shaped orbits. But if we have a mostly circular orbit, we can call it the radius of the orbit. So, or essentially the distance of the planet to the moon, or the asteroid to the moon, or dwarf planet to the moon, whatever. And then you have the combined mass of the orbiter and the orbited. The cool thing that we can do with this is oftentimes you can do some algebra, and you can just move mass over to the left side and move period over to the right. I'll leave that as an exercise to the audience to do that. But you can figure out mass. But you've got a combined mass, m1 plus m2. Usually, though, the mass of your moon or the orbiter thing is usually so much smaller than the thing it's orbiting that you don't have to consider the mass of the moon or the mass of the satellite or the mass of, say, like maybe a planet going around a star. So we can this is how humans figured out the mass of the sun. It is also how we figured out the mass of all of the planets in the solar system, except 2. Does anybody know which planets don't have moons? Venus does not have a moon, right?
One more.
Yeah, yeah. Mercury also does not have a moon. So in fact, we did not know the masses of Mercury and Venus very well until we sent space probes, which were little artificial moons. And then we could figure out the masses of those, because then that moon or that planet, or, you know, like we can, this is also how we figured out like the real mass of our own moon, is we can send a space probe or something there and use that space probe as the moon, little m2, so it's like massive moon, and then the mass of the world, the orbited thing, is m1. So yeah, space probes are great for that. So that's all. Like, people were a little concerned that maybe they were gonna, because we didn't have a really good mass for Mercury or Venus, people didn't really know, like, are we sending this on the right trajectory? Are we going to like blow right on by it? You know, until we had those orbiters, we couldn't figure out the mass of something, of those worlds. So anyways, but because a lot of worlds had moons, like especially all the giant ones, it was relatively easy to figure out their masses, because you can also use a little bit of geometry to figure out how far away that world is from us. Because remember, one of the things that you have to do is have distance from the gravitational source. So you have to figure that out, and you use geometry for that if you're in the solar system. Or we could use radar ranging, which is one of the things that we did with like Venus and Mercury to also figure out their rotation rates. You can bounce radar off of them and then see how long it takes to come back. But we can also use just like some plain old geometry to do, or trigonometry even, the triangles, using the geometry of triangles to figure out the angular size, and then you can figure out some more information from that. So moons, I mean, like, this is just one thing, and we don't even need to know anything about the surfaces of the moons. We just need to know where they are, how long it took them to go around. So, which is amazing. And then from those kinds of things, we've now figured out, astronomers have figured out now, oh, that didn't show up as well as I wanted to, how many moons there are in the solar system. And this is purely just from pictures, okay? So we have our, in the top row, if you can't see it, we've got our planets, our 8 classical planets, okay? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and have the currently known moons. Now, I'll say I got the list. I got it from Wikipedia. I love Wikipedia. I think it is amazing. You should totally use it for astronomical information. I'll leave it to you to figure out what other sorts of information you can use. But astronomical information is totally great. There are so many nerds out there who love to put up things from press releases and stuff like that. Use Wikipedia for astronomical stuff. It is awesome. All right. So so we've got our moons up there for the planets up on the top. And then notice that like Saturn has a little question mark there. Because the thing is that you could consider, and I mean, really, we could maybe put that for all of the giant worlds, because the rings are actually bunches of rock, which are little tiny, you could call them moonlets. Okay? And the rings of Saturn even are they're icy chunks of, that are range in size from pebbles to, a kilometer wide or whatever, like meters in size. And then they clump and unclump and reform and make little like things all throughout the range. So you could call like every single thing orbiting Saturn a moon, but then we would be in the millions to billions of moons. So we got to cut it off somewhere. All right. So that's, there is a cutoff, and that means that Saturn has 146 right now. If you look at Wikipedia, you can actually find like when the different ones when all these new ones came on. There's an amazing list of this Wikipedia page that I have on here, which is the list of natural satellites. It has so many. Oh my gosh. And it has little pictures of all of them. It's totally cool. So anyways, then the next one has consensus dwarf planets. So when the International Astronomical Union made in 2007 made the definition of a dwarf planet, they named 5 of them: Ceres, Pluto, Haumea, Quaoar, and Makemake. Or no, Eris and Makemake. Sorry, Quaoar was not one of them. But they did not make a way to add more. So there are still only 5 official dwarf planets, but the people who study them say like these other ones should be included especially because they're rounded. That's like one of the biggest things. They're rounded and they go around the sun. So, but I want you to notice something with these worlds. So dwarf planets are all small. There are, in fact, 7 moons larger than Pluto, which is one of the biggest dwarf planets that we have. Eris is maybe the same size. But all of these dwarf planets are small. But look how many moons they have. Almost every single one has a moon, except for Ceres, which is the one that's in the asteroid belt. All these other ones are outside the orbit of Neptune, also called trans-Neptunian objects. And they have so many things. Like they have lots of these orbiters. So that is another interesting thing. And that's another thing that we can talk about with moons in just a minute. But then there's also, if we want to think about other moons, we can think about moons of minor planets. And so trans-Neptunian objects, like all the dwarf planets, are included within this category of minor planet. And this is why I was talking about nomenclature a little bit ago. So anyways, there are like 500 moons around minor planets that are known so far. And we're adding more all the time. So in fact, this particular resource that I went to was most recently updated in January of this year. And if you actually look at the Wikipedia page, it wasn't as updated. I know. We need a good nerd to go in there and change that number. So the most recent one in Wikipedia was from 2022. So, it's a thing that you can think about, but there's this person who does this, like that's part of their job, is to make this catalog. So anyways, that's something. So this is something that's kind of interesting, and it's an interesting thing to kind of notice these different worlds, like what kinds of worlds have lots of moons, and that brings us, it brings us into thinking about planetary formation. But I did want to talk about a few other things first, dealing with moons, because this is actually kind of I love this montage. Created by Emily Lakadawala, who was at the Planetary Society. She's out on her own now and writing books and stuff. But these are all the round objects in the solar system. It's totally cool. It looks so good, I think. And one of the things I like about it is they're the right size compared to each other. So this is really an awesome. If you go to the Planetary Society website, you can find this in there. And you can maybe see, like, for instance, there's our rocky worlds. Actually, the rocky worlds are maybe, you know, they're all, the contrast is enhanced on all of them to make them stand out a little bit more. But these are things that are actually round. So they're not potatoes. Okay, so these are the not potatoes of the solar system. And so we've got kind of like our one moon here for Earth, but Mars doesn't have any round moons. It actually has potato moons. It has little asteroids. So here's Jupiter's 4 large moons compared to it. The Galilean moons, because those are the ones that were first discovered by Galileo using his telescope. And then he published his data. That's a big thing to know, right? He published his data. He didn't, there could have been other people who saw the moons, the same moons, but he's the one who published widely. Uranus with its moons, Saturn and its moons. And then if we actually just take away most of our big worlds, we get to our, just like this is the moons of the solar system compared to each other in size. And I did find this one on Wikipedia. It's most updated on Wikipedia. And I like this one because it shows the sizes compared to each other. But then it also shows you different names. I don't know if you can read these super well, but Earth, moon, right? Okay. Luna. Mars has moons, and all of these things are associated kind of with each other. So Mars's moons are Phobos and Deimos. Mars is the god of what? War, right? And so Phobos and Deimos are fear and panic. Okay, which were 2 of the things that followed Mars around all over the place. Jupiter's moons, largest moons, Io, Europa, Ganymede, Callisto. Other moons are named like Almathea, Metis, like all these things. They're all Jupiter's lovers, girlfriends, and boyfriends. So Ganymede was a boy. And supposedly the most beautiful, you know, male of the species. And was brought up to be the cupbearer. Yeah. And up to Olympus. So there's like lots of, like, these are named from mythology. Now the thing is, none of these moons, besides our own moon, were known until the 1600s. Okay, because you have to have a telescope to see them. And so all these names were done in the 1600s and later. So that's kind of a thing to realize. So Saturn's moon, Mimas, Enceladus, Tethys, Dione, Rhea, Titan, Hyperion, Iapetus, Phoebe. Yeah, these are all names of Titans. And Saturn, does anybody know what Saturn's Greek name is? Yeah, Kronos, right? And so Saturn, or Kronos, was Jupiter / Zeus's father. So the next one out, right? And also was was kind of the head of the Titans. And so all the moon, so the first moon was named Titan because Saturn was Titan. And so, and then all the other ones were various other Titans. So, I mean, there's like Polyphemus in there. There's Hyperion, all sorts of other cool things. Then we get to Uranus, which is kind of interesting. Puck, Miranda, Ariel, Umbriel, Titania, Oberon. Does anybody know what those are from? Yeah, Shakespeare, right? And so all of them are named after these Shakespeare characters. Remember, 1600s and later. So, well, you know, I mean, Uranus's moons were pretty hard to find, and so they really are more like late 1700s, 1800s kind of thing. You needed a bigger telescope for those. Neptune, and then Uranus, by the way, is Greek.
Name is Uranus,
Mm-hmm.
which is like the Greek name. I think he was the father of, well,
right? He's the father of Saturn in Latin, or Kronos, right? Also known as the sky, right? So I think that because they'd already gone through all the Titans and they'd gone through all of like Jupiter's, paramours, and that they needed something else, and so they went with something like well known in Shakespeare. And then Neptune, we've got Proteus, Triton, and Nereid. And so Neptune is the god of ocean, water, Greek name of Poseidon, right? And so Triton was his son. Little Mermaid fans here, right? This is the way that I always remember, because there is Triton of Neptune and Titan of Saturn, and they are nothing like each other except they are both moons. And so Triton and Titan are very easily to mix up, and so I always have to think Little Mermaid. Whenever I think of any moons of Neptune, Little Mermaid, right? And so all the other ones are named after various mermaids, except for Proteus, which was kind of the previous, it was the Titan god of the sea. And then Pluto's biggest moon is Charon, and Charon was the ferryman across the river Styx, and then various other moons of Pluto are named after underworld things. And so then, but there are also other things like Eris. Eris's moon is named Dysnomia. And so Eris was the goddess of discord, and Eris has caused so much discord amongst astronomers and planetary scientists. So, but Dysnomia was a companion of the goddess of discord, and so like all the there's always some sort of association. Actually, the original name of Eris was Xena, after the warrior princess, and so her moon was Gabrielle. Who was her companion. Any Xena warrior princess fans out there? So anyways, but like I wanted you to kind of know a little bit about the way that the moons have been named. And otherwise, they are named in order of discovery. So for instance, the Jupiter moons, actually the Galilean moons, are named for how far, their order from Jupiter, the first ones are, but all the other ones have been named in order of discovery. So that would be like Jupiter 10, Jupiter 11. And so it doesn't really have anything to do anymore with how far away they are. So then other things that moons can show you, they can show you age. They can show you some things about age. And so when we look at things like for age, we have two big things. One of them is cratering. So when you look at, this is our own moon, we have the near side and we have the far side. I'm going to talk about that in just a minute. But the near side, you see that it has some patches kind of on it, some dark patches. Those are called the mare. So mare means ocean in Latin. And the plural is Maria. It looks like Maria, but it's Maria. And then notice that the far side doesn't have nearly as many Maria. It has a lot more craters. And the thing is, if you have craters, that means that a lot of craters, that means the surface is old. Otherwise, if there are very few craters, that means the surface is young. Because in the early solar system, especially, there was a lot of stuff flying around, and so there was a lot of impact events, and so you had to have something be able to resurface the planet. So our Earth has very few craters that are visible on its surface, because we have lots of things to erase them. We have plate tectonics. We have lava that can erase them. We have erosion from rain and rivers and oceans and all that kind of stuff. So we have a lot of resurfacing ability. But we have other things, like this is Enceladus, one of Saturn's awesome moons. And so one part of Enceladus, this part up here, has relatively a lot of craters compared to another part of the world. And so that surface is likely older. And then the surface down here, the tiger stripes terrain, in the lower part of the image is younger because it doesn't have a lot of craters. So we look at the number of it's like the crater density per unit area to kind of figure out a relative age. The awesome thing about the craters, or the lack of craters on Enceladus, is there are plumes of material that are coming out and then helping resurface that surface. There are other worlds, I'm going to talk about those in just a moment, but that's another thing. If we go back to the moon, for instance, also there's the darker areas, the mare, are very smooth. If you ever see these through a telescope or anything, or see like close-up pictures of the moon, or zoomed in pictures of the moon, you'll see that there's very, very, very few craters in those areas. And that's because that was actually a basaltic lava that flowed over a whole bunch of craters and covered them up to make them not seen. So yeah, it erased it. Now, the thing that I want to say about near side and far side is that every single moon in the solar system that is round, so not potato moons, right? So we're not talking about any potatoes. We are talking about the rounded moons. Every single one of them is looking, or has the same face toward its planet at all times. It's called synchronous rotation. And it means that one day on that moon is exactly equal to one orbit. Synodic. Okay. But the reason for that, it's a tidal force thing. If you want to talk about that, I would totally be happy to talk to you about that. But we always see the near side. We always see the same kind of like man in the moon shape, or the bunny, or the woman, or whatever you want to call it. But we always see that same side because the Earth or the moon, as it goes around Earth, it's not spinning that fast. It's spinning pretty slowly, but it's always facing the same face toward Earth. Every moon in the solar system does this. So every single moon has a day that is equal to its orbital period. So if we were to have a moon base and we wanted, say, solar power, you would have half of a month, because remember, a month, right? So we would have half of a month of solar power and then half of a month of dark, because how things go around. And that's why I say near side and far side. I do not say dark side, because the far side of the moon does totally get lit up. It's lit up every new moon, right? Or it's like totally lit up. It's like fully lit every new moon. So yeah, it's like, because that's the side that's facing the sun. The dark side is facing toward us, which is also our near side. So the near side is sometimes dark and sometimes light, and that's why we have moon phases. So anyways, that's like a really awesome thing to think about. So you have, with moons, you have this one way of dating a surface is by craters. The other way, and this only works in the icy outer worlds of the solar system, is called radiation darkening. So ices were, this gets into kind of planetary formation. There's a lot more ices toward the outer part of the solar system. It was just too hot for them to be close to the sun. That's why we have rocky worlds close to the sun, and we have, gassy and icy worlds far away. So these rocky worlds, craters are pretty much the only way we can date or age the surface. But when you get to these icy outer moons, then we get to use radiation darkening. And one of the reasons why I want to use Io, Europa, Ganymede, and Callisto that are going around Jupiter is you can really kind of see, because they actually go in order from closest to farthest if you go from top to bottom. So Callisto is the dark moon at the bottom there, but it has these light splotches on it because that's where there have been impacts. And you've gone under a radiation darkened thing, I'll talk in just a second on that one, to the ice that's underneath it that turns bright white. So on the surface, because some of those ices, we got water ice, ammonia ice, and methane ice. Methane is carbon and hydrogen. If you expose carbon or methane to ultraviolet radiation, then it breaks into pieces, and you get hydrogens and you get some carbons. Well, if you have a whole bunch of carbon, you put that together and that makes like soot or graphite, essentially, which is a whole bunch of carbons. Graphite is carbons. And so then it turns everything darker. So when you have ices, you get darker surfaces. So the darker the surface, the older it is when you have ice associated with it. So if you look at pieces of, say, of Callisto, you've got some parts that are bright white, so they're younger, and then you have some pieces that are really dark, which are older. And then Europa, which is the one, the second farthest of the Galilean moons, is usually pretty light. This is actually contrast enhanced, is usually pretty light colored, and it has almost no craters also. So it's both craters and radiation darkening tell you how old that is. And so and then like Ganymede has its own thing too. So like it has darker areas and lighter areas. So radiation darkening tells you about the ages. And then also, when we look at moons, we also look at geology. And so this kind of like brings back what I was just talking about, where you have rock geology versus ice geology. So we have two worlds, Mercury and Ganymede, which are almost identical in radius and like pretty close in mass. And you can get, and they look very different. So Mercury is really highly cratered. It doesn't really have any smooth areas at all on it. But Ganymede has, it has differences in color. So it has radiation darkening going on. And it also has differences in the number of craters. And so there's a lot, a lot more kind of action going on Ganymede, even though both of them have been hit by a lot of things. And so we've got that kind of geology because the way that you heat it, this is something that people did not know before we actually sent space probes. Because remember that the images that we were getting from Earth were more like this, right? They look like bright little dots. We didn't have a lot of stuff until we started going with space probes. So the Voyager spacecraft especially sent back amazing, amazing stuff. And we started seeing that these worlds were way more interesting than we ever had dreamed. And so because a rocky world, the way that you make a world hot is through forming it, and you have what's called differentiation, where dense stuff goes to the center and light stuff floats to the top. So that's why we have a really dense core, like iron and nickel in the core of our Earth. And then you have kind of like we have some of that, but we got sand and all that kind of stuff on the silicate crust. So you have differentiation, so where denser things go sink to the center and lighter things float to the top. And so that actually causes friction, it causes heat on the interior. And then you have stuff smushing together. Well, that doesn't happen. There's not a lot of that. And so, especially nowadays, so we don't really have that too much. And then you have radioactive decay on the interior of the world. And so, actually, I suppose I should show that. But there's these three things. And that's what the little flashes kind of are in this little diagram. Like these little things right here are the little radioactive decays. And the thing is, if a world is small, it has a lot of surface area compared to the volume inside. And it releases its heat more easily. You can totally see this with ice cubes. If you have like a little bitty ice cube, like those little like crushed up ones and stuff, they really make your drink like cold fast, and they melt really fast also. And they're like easier on your teeth when you chew them. Then if you have like a big chunk of ice cube, it takes a while for that thing to melt because it has not as much surface area compared to the volume inside. So the smaller the world, the more heat it will release. So a world like Mercury, a world the same size as Mercury, should be just as dead as Mercury because they have the almost identical surface area to volume ratios. But Ganymede has something different. It has tidal heating. So there is an orbital resonance with the Galilean moons, or at least the inner three, Io, Europa, Ganymede, and Ganymede, and they have this this orbital resonance where for every 4 times Io goes around, Europa, for every 4 times Io goes around, Ganymede goes around once, but Io goes around twice, right? Or Europa goes around. Oh. Jeepers creepers. The numbers are there. So for every 4 times Io goes around, Europa goes around twice, and Ganymede goes around once. And so that doesn't mean like Io and Ganymede are like having a little tug of war, or like Ganymede is tugging on Io, in relationship to Jupiter, because Jupiter is always going to win, right? Jupiter has 318 times the mass of Earth, and Ganymede is about the size of our moon, right? So it does not have a lot of mass. But what is happening is these moons have been pulled into slightly elliptical orbits. Their orbit is a little bit squished. So sometimes that moon is closer to Jupiter than it is at other times. And that causes it to get more, when that moon is closer, it causes a stretch. And then it gets not as stretched. And then it gets stretched. And then it gets not as stretched. And then it's stretched. Well, if you've ever like squeezed silly putty or a tennis ball in your hand, you know that it heats up after a while. That is exactly what's happening on these moons. So Io it is the most volcanically active world in the entire solar system. These are some, of course it's not going to run. The upper image is one from the Galileo spacecraft, which is which actually shows active lava like going on. Like there's a lava lake right there. And then these white areas, by the way, that's just where the detector was overwhelmed. There's like no data there. So it was really hot there actually, but it just kind of overwhelmed the detector on the Galileo spacecraft. So, and then there's a little movie here that is not playing. Oh, there it goes. This is an artist's conception from some Juno imagery that was just put out in, oh goodness, when was this? You might have seen this in kind of March. But there is a lake as smooth as glass. It's basically like an obsidian lake. And let me see if I can get it to play again. There we go. And so then there's an island kind of in the middle of it. So this is an amazing, amazing world. And the reason why you see you see that kind of reflection in there is because when the Juno spacecraft went around Io, it saw the reflection of the sun in this lake. So it's showing like as smooth as glass, right? So it's a mirror. It's like a mirror there. It's totally amazing. So you can go to NASA to find out more information about that. And then there are a couple other things that I wanted to say. One of the things is like the Uranus, like when we think about different moons, because I'm going to have to end here in just a minute. When we think about different moons, like all these Uranus moons, they're all relatively small. And the thing is, you are always going to see the exact same pictures of them all the time. You will never see any different pictures than these. These are the highest resolution images that we have because there has only ever been one spacecraft that has ever gone to Uranus, and that is Voyager 2. Same thing with Neptune. There's only one spacecraft that has ever visited, and it was a flyby. Both of them, both Uranus and Neptune, were flybys. So they got their one image, whoop, 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 and then they had to go on. Okay, so same thing also with Pluto and its moons. We only have those images, and we are not getting any more until we actually send things out to them. So send more things out. But these are all the highest resolution images that we have. There is one other thing that I kind of wanted to bring up here. When we think about planetary formation, you can actually kind of tell a little bit about some of the worlds by how big their moons are. So if you're thinking about mass of the worlds, Earth has an unusually large moon. Like, we should not have a moon as large as we did. We do. The thought is that we got impacted by something enormous. And so if you ever want to find out more, type in YouTube how the moon was born. It's totally amazing. But Jupiter, being the most massive world, has 4 large moons and a whole bunch of tiny moons. And then Saturn has 1 large moon, a bunch of medium-sized moons, and a ton of tiny ones. But it also has like a just giant ring system. That's why the little question mark is there. Then Uranus has no large moons, and it has 5 medium moons. So medium means that it's round, but it's not bigger than Pluto, essentially, was like my criterion. But really, it's round. So if it were in orbit around the sun, it would be a dwarf planet, which is kind of an interesting thing. And then Neptune has this kind of weird thing going on. It has 1 big moon, Triton, but no medium-sized moons. When its twin, Uranus, has a bunch of medium-sized moons. The thought is that Triton, I almost screwed up Triton. Titan is a world that we think was captured. It's going around Neptune the wrong way, for one thing. It should be going around the same direction that Neptune is spinning, and it's totally not. It's going the other way. And it is slowly falling into Neptune. It eventually will become a spectacular ring system when it gets tidally ripped apart. But in several 100,000 years, okay? Not like immediately. So so when when you figured out the Fountain of Youth, then you're definitely going to get an awesome show. But anyways, the thought is that it is a captured Kuiper Belt object, like Pluto. It's like almost a Pluto cousin, and it threw out the medium-sized moons or caused them to crash into Neptune. That's one thought. It has to do with planetary formation, like how we think everything formed from a giant cloud of gas and dust. So on the right is an artist's conception from data from the European Space Agency, European Southern Observatory, and the James Webb Space Telescope. And then there's actual data from ALMA, which is the Atacama Large Millimeter Array of telescopes. And it is, so this is like actual data on the left and artist conception on the right. And so when we get farther out, we have a lot more ices combined with the rocks and metals that were also in the planetary system. But that also does. But the thing is like when something is closer to the gravitational source, it also moves around slower, which kind of brings me to the trans-Neptunian objects that I wanted to say a little bit more about. Almost all of the known trans-Neptunian objects, these are the largest. These are the ones that are they're rounded, right? So they're probably dwarf planets. But remember, there's only 5 official ones, and one of them is in the asteroid belt, so it's not listed here. So the 4 on top are the 4 dwarf planet trans-Neptunian objects, which are things outside the orbit of Neptune. So this is like an icy asteroid belt outside the orbit of Neptune. And like, notice they have like a lot of moons. One of the reasons why people think this is happening is because things are orbiting so slowly out there. If there was something near them, they grabbed it, and it just kind of kept going together. They made friends. They're very, they mosey, so they make friends easily, right? So yeah. But a couple other quick things I wanted to just say about moons and how they're like super amazing is sometimes they can, Saturn's moons have 2 really awesome moons that are shepherd moons. They kind of make a ring kind of come together. Another thing with Saturn's moons, they can be little gap moons, and they can create 3-dimensional perturbations in the ring system. And the reason why we see this was when there was Cassini was going around Saturn, and it went around for like 16 years, and it got to see the rings being exactly aligned with the sun, And so then I got to see shadows. Oh, it was amazing. But then we also have like this other amazing moon. Sorry, this is another amazing moon, Titan. Titan, which goes around Saturn. It's the only moon that has an appreciable atmosphere, and that atmosphere is 1.5 times Earth's atmosphere. And the only way we can see through it is through radar. And there have been some amazing things found. There are lakes of methane and ethane on there because it's so cold. And then when we sent the Huygens space probe down through those clouds, and this was several years ago, but here is a watershed, like a river, like streams coming into a river of methane and liquid methane and ethane. It is so cold on Titan. And then the other amazing thing, like look at these rocks. These are rocks that are rounded. The way you get rounded rocks is by having them moved by wave motion. If you get a whole bunch of them, like there's all these rocks. This is how you get, these are like shoreline rocks. Otherwise, you have kind of like really jagged, if they're just like broken up rocks, they're really jagged. So these are like earth rocks up here on the top. And then these are the Titan rocks. And so there was likely an ocean there at that time, and it could be just like it's not the right season for having like a lake right there. It's totally amazing. And then we've got Neptune's interesting moon, which we've only seen the one time, right? And it has like little wind streaks. It has some maybe frost deposit. It has cantaloupe terrain, which nobody had ever seen before. This is amazing. So these worlds are this wealth of awesomeness. And the thought is that there are several of them that are what we call ocean worlds, where they have something underneath their icy crust. Because of tidal heating, they've been able to melt some of their ice, and maybe there can be habitats underneath there. If you're interested in learning more, there are some really amazing resources. I highly recommend the Silicon Valley lectures on YouTube. They are for a general audience. This is like super cool if you want to take a picture of that. That one, that's totally worth taking a picture of. I love the Silicon Valley lectures. You can also, if you want to, like the Harvard Smithsonian Institute for Astrophysics does show its colloquia, but those are for astrophysical audiences, okay, not necessarily for the layperson. But the Silicon Valley lectures are for the layperson, right? An interested person. I highly recommend those. And I highly recommend Wikipedia. I got several of my pictures from the NASA Photojournal, which is run with the Jet Propulsion Laboratory. And that has it is the definitive place to find images from NASA missions, along with captions. And they're awesome, like all the ones that are put out by press releases. Also, the Scientific Visualization Studio is really, really, really cool. It is the NASA Scientific Visualization Studio. It has all sorts of amazing animations with really great, some of them even have like lesson plans with them and stuff. So with a lot of really great captions and stuff. And then the Planetary Society has a whole lot of amazing pictures. There's a whole collection of them. So I would really highly recommend that as well. So with that, I hope that you've learned about some amazing things that we can learn about moons, and then that you'll go find places to find some more. Thank you very much.
All right. Fantastic talk.
Thank
so
you.
I'm going to start the Q&A session. What is your favorite moon to talk about?
Ooh, my favorite moon to talk about. I mean, there are so many that are so amazing. But I would say it probably has to be Europa, because I love to think about what could be underneath that ocean surface, or that icy surface. There is more water underneath. The thought is that there's more water underneath Europa's crust than there is here in Earth's oceans. And there are so many living things in Earth's oceans, even when you go down to like the Challenger Deep and stuff like that, like Marianas Trench and stuff. And then there's so much heating with Europa. There's probably black smokers and things like that. What kind of things could be there? Oh my gosh, that would be so cool. So
Definitely.
yeah, if you ever have it, another really amazing talk that I highly recommend is by Dr. Kevin Hand he's actually a NASA deputy director of something or another, but he has this really great talk about ocean worlds, and like it's amazing. So I highly recommend that as well. He gave it to JPL, the Jet Propulsion Laboratory. So if you're interested, maybe we'll put that in the YouTube thing.
Right.
But anyways.
So we'll open up the floor to questions. I do have the microphone we're going to pass around so that everybody can hear the questions. Everybody on YouTube can hear the questions. So if you have questions, go ahead and raise your hand there. Or maybe as we're thinking of questions, there was one that came up on the chat. How big does one of these space potatoes have to be in order for gravity to finally squish it into a ball to make it one of the round moons?
Yeah, so space potatoes are you definitely have to think about what they're made of, right? So they're not all made of the same thing. So if we're talking about asteroids, we're talking about like rocks and metals, essentially. They have to have more mass than one of those Kuiper belt objects, which has ices in it as well. So the ones that are the icy space potatoes don't have to have as much mass. But we're talking about, honestly, I mostly think of them in radius. Kind of you have to have ones that are probably Tennessee sized, essentially, to be round enough. So.
Got a question up here.
How did moons get their names?
Oh, how did moons get their names? Mostly it was, that's a great question. So some of it was for the people who discovered them. So they always suggested names. So in fact, Galileo tried to name the four Io, Europa, Ganymede, and Callisto after his patrons, the people who gave him money. You know, he's like his funding source, right? So, but people did not like that. They didn't think it was good enough for for the future, for posterity. So then for a long time, actually, they didn't have any names. They were just named Jupiter 1, 2, 3, and 4. And then it just kind of was like part of the literature. They were like, hey, wait, we should name these things, especially now that there are more of them, because they were kept discovering more. And so then they just decided to name them after, things that were associated with those planets.
Okay, thank
So
you.
you're welcome. It's kind of a longer answer than maybe needed, but.
Do you know anything? What is Zoosfay?
What is what?
Zoosfay. 202 VE.
Oh. That one, 202 VE? No, I don't. I guess I still don't know what you're talking about.
It's a moon-like thing in orbit around both Venus and the Sun.
That one, yes. So there's a thing that is thought to be like a Venus-ish moon or kind of a Neptune moon. It's usually called a co-orbiter, right? So it's a thing that does not seem to go around any one of those worlds, but it is a kind of like another small body that kind of is near the same orbits. This one is, and I gotta say, I don't remember it's exactly how you say. You struggle with a name. I also struggle with that name. So it may or may not be real, but if it were, it would be like a co-orbiting thing and a small thing. So yeah, I don't have a better answer than that, but it's a cool thing to think about.
Other questions? Nathan, were there any others on the YouTube chat?
No, I don't think anything's come in.
Oh, we got one over here. Okay.
I'm a big Eris fan.
Ooh, excellent.
So I'd love to know if you feel like sharing some of the strife and discord that she's caused in the
in the
world.
astronomical community,
Yeah.
right? So this is, so Eris is the goddess of discord. And I think that this was like I think it's one of the best names that astronomers could really have come up with for this world, because Pluto it all has to do with Pluto. And so Pluto, ever since it was discovered, people were like, wait a minute. This has ended up being really small. And then once its moon was found and the mass was determined through the greatest equation in all of astronomy, they were like, wait, this is really small. I don't know if we should call this a planet anymore. What if we find other ones? People were like, nah, we're not going to worry about that until we find it. Well, there was found another world that was about the same size as Pluto, about the same distance. And so we really had to decide, all right, are we going to be naming these things, like, are we going to have more planets, or are we going to try and reclassify? Now, the thing is, the reclassification has happened before. It happened with asteroids. So back in the 1800s, there were like 12 or 13 planets in our solar system, because asteroids, the first asteroids discovered, were also called planets. So then once their masses were determined, or, roughly determined, people were like, okay, we're going to start calling these things something different, and took them away from planethood. And so they're still there. Like, Eris is not gone. Or Pluto is not gone. But Pluto is one of the most amazing worlds in the solar system. But it is one of a class of these Kuiper Belt objects. They're these icy, worlds outside the orbit of Neptune that are so cool. Like, if another really great YouTube video is Dr. Alan Stern talking to Purdue about what if we go back to Pluto. It is amazing. Like, he was the project scientist. He was like the project manager of the New Horizons mission. And so gives a really great timeline of what happened, and then the awesomeness of the science of Pluto. That was one of the biggest factors in making Pluto pretty much my favorite world in the solar system now. So when I was like, meh. But so the discord was, okay, are we going to be like planet or not planet? And then when the IAU came together to talk about it, the International Astronomical Union came together to talk about it, to try and define planethood. Oh my gosh, that's been a huge thing. And planetary scientists do not necessarily agree with other astronomers who, they're like, why are you talking about our jam here, right? We are planetary scientists. You people who study stars and galaxies and stuff like that, who are also members of the International Astronomical Union, you shouldn't be deciding our nomenclature. And so, there's a lot of strife that kind of is still going on. I don't know. But, so discord, lots of it. And, one of the biggest books by Dr. Mike Brown, How I Killed Pluto and Why It Had It Coming. That's also a really good lecture to look at too, but on YouTube. But yeah.
Anybody else? Oh, one other.
So the distance between the moon and Earth is used as a kind of a measurement unit, but that distance changes throughout the year. There's the perigee and the apogee. So how did the astronomers decide what that unit is going to be?
Oh, yeah. So it is the average lunar distance. So that's a great question. It's the average lunar distance. And so that distance doesn't change too much. It changes by a couple of Earth diameters, essentially. So instead of saying 30 Earths in between, it's about 28-ish versus 32. So that's about so the moon's orbit is not circular. It is oval shaped. So yeah, but it's the average distance. And that for all of the worlds, it's their average distance is the one that the distance I have in this table.
Any final questions?
And I am happy to talk afterwards too, while people are looking at the telescope.
Yeah. So I'd be remiss if I didn't mention a little bit about one moon of Jupiter. So the first 4 moons of Jupiter were discovered by who? Galileo. Who discovered the 5th? So there was a guy named Edward Emerson Barnard. A lot of things are named after him, like Barnard's Star, Barnard's Loop, Barnard's Galaxy. There's an exhibit up at the front lobby about Barnard. Anybody want to guess where he was born? Say it. Nashville, exactly right. So a little bit of history here, right here in Nashville with Edward Barnard, and one of his many discoveries was the moon Amalthea, the 5th moon of Jupiter, which would also be the last time anybody would discover a moon just by looking into the eyepiece of a telescope. So kind of fun little trivia. If you want to learn more about that, you can always ask me later. But
yeah, and otherwise they would discover them by using photographs or digital cameras.
Or flybys.
Yeah.
So let's give Dr. Grundstrom a huge round of applause for another fantastic talk. So yes, if you'd like to go up and see the telescope, you're welcome to. There are passing clouds, but if we do have some clear spots, we're looking at a double star. We talked a little bit about double stars tonight. It's a really nice double star in Virgo called Parima. And when you look in the telescope, well, in the night sky it looks like 1 star, but in the telescope you see it's actually 2 stars that appear very close to one another. So it's really pretty. And of course, if you haven't seen the telescope before, you got to go up and see that, even if it is clouded out. But thank you all again for coming this evening. Be sure to check out our website. Follow us on Eventbrite. We hope to see you up here again. And thanks to all those at home that were watching on YouTube. So if you have more questions, Dr. Grundstrom will be here for a little while. And if you have any other questions, be sure to ask myself or one of the other staff members or volunteers. So hope you all have a great night.